For millions of years deep inside the dense R136 star cluster, one stellar giant has been burning with almost unimaginable power. R136c, a Wolf-Rayet star so hot and luminous, it pours out more energy than millions of suns combined. Its fierce winds strip away its outer layers, sculpting the surrounding nebula and pushing its life toward a spectacular, inevitable end. Today, we explore what makes this monster star so extreme, and what it can tell us about the most massive stars in the universe. If you enjoy journeys to the most extreme stars, please like, subscribe and share, and tell us in the comments what fascinates you most about a star burning with the power of millions of suns. Thank you for watching. Now let's begin. The Large Magellanic Cloud is a nearby dwarf galaxy that orbits the Milky Way and provides the wider galactic context for R136c. It lies at a distance of around 160,000 light-years, close enough that individual star-star clusters and nebula structures can be resolved in detail with modern telescopes. It is classified as a Magellanic spiral galaxy, with a central stellar bar and a disk that appears irregular compared with the more symmetric spiral pattern of the Milky Way. Its total mass, including dark matter, is smaller than that of the Milky Way, but still substantial for a satellite system, and it is currently considered the most massive satellite galaxy of the Milky Way. Kinematic studies indicate that the Large Magellanic Cloud is not simply a static companion, but follows an orbit that is being reshaped by mutual gravitational interaction, and simulations suggest that it's likely to merge with the Milky Way in a few billion years, for the purpose of studying R136c. What matters is that this galaxy offers a nearby lower metallicity environment in which very massive stars form and evolve. The stellar content of the Large Magellanic Cloud spans a wide range of ages, from ancient globular clusters to very young associations containing massive O-type stars and compact clusters. Surveys count tens of billions of stars distributed in a disk bar and extended stellar halo. The gas and dust content is high for a dwarf galaxy, with large reservoirs of neutral and molecular hydrogen that sustain ongoing star formation. One of the most important properties of the Large Magellanic Cloud in this context is its lower abundance of elements, heavier than helium compared with the Milky Way. This reduced heavy element content affects the opacity of stellar atmospheres and the cooling properties of gas clouds, which in turn modify how stars form and how they lose mass through stellar winds. In particular, the lower metallicity tends to reduce line-driven mass loss for hot stars, allowing very massive stars to retain a larger fraction of their initial mass during the hydrogen burning phase than comparable stars in a more metal-rich environment. This makes the Large Magellanic Cloud an efficient site for the formation and survival of extremely massive luminous stars like those found in the R136 cluster. The spatial structure of the Large Magellanic Cloud shows signatures of its interaction with both the Milky Way and the Small Magellanic Cloud. The stellar bar is offset from the geometric center of the outer disk, and the disk itself appears warped and thickened. Streams and bridges of gas connect the Large and Small Magellanic Clouds and extend into the Milky Way halo, tracing the effects of tidal forces over long timescales. Neutral hydrogen maps reveal a complex distribution of gas, with high column density regions coinciding with major star-forming complexes. These interactions influence the global star formation rate by compressing gas in some regions and stripping it in others. They also affect the dynamics of the outer halo and the orbits of clusters and associations, but the inner star-forming disk where the Tarantula Nebula and R136 reside remains a region of intense ongoing star formation. The Large Magellanic Cloud hosts numerous stellar clusters and associations that sample a wide range of masses and densities, making it a useful system for testing theories of cluster formation and evolution. Observations identified dozens of globular clusters, hundreds of open clusters, and many loose associations of young stars. Among these, a subset of young massive clusters stands out because their stellar masses, ages, and central densities resemble those inferred for young globular clusters in the early universe. These young massive clusters provide conditions under which very massive stars, possibly exceeding 100 times the mass of the Sun, can form and interact in dense environments. The Large Magellanic Cloud is therefore not only a nearby example of a low metallicity galaxy, but also a system that hosts some of the most extreme star-forming environments accessible to direct observation. Star formation in the Large Magellanic Cloud is not uniform across its disk. It is concentrated in several prominent complexes, of which the region known as 30 Doradus, or the Tarantula Nebula, is the most active. This complex lies in the northeastern part of the disk and dominates the current star formation output of the galaxy. It contains giant ionized regions, dense molecular clouds, and multiple generations of young stars. The ultraviolet radiation and stellar winds from young massive stars in these complexes have a strong impact on the surrounding interstellar medium, creating bubbles, shells, and cavities in the gas. Although this section does not yet focus on the detailed properties of any specific nebula or cluster, it is important to note that regions like 30 Doradus demonstrate the capacity of the Large Magellanic Cloud to sustain high rates of massive star formation in a relatively compact area. The same galaxy also provides crucial benchmarks for distance measurements and stellar evolution models. The presence of numerous Cepheid variables, red clump stars, and eclipsing binaries allows multiple largely independent methods to calibrate its distance and to test how stellar properties depend on metallicity. Supernova events such as the well-studied supernova in the late 1980s have supplied detailed information about core collapse physics and the surrounding circumstellar and interstellar environment in a low metallicity setting. Each of these constraints improves models of how stars evolve in the Large Magellanic Cloud, and by extension how very massive stars like R136c are likely to behave under similar conditions. The chemical composition of the Large Magellanic Cloud interstellar medium has also been studied in detail. Spectroscopy of H2 regions, planetary nebulae, and young stars indicates that the overall abundance of elements such as oxygen, nitrogen, and iron is lower than in the solar neighborhood, typically by factors of around 1/2 to 1/3. This lower heavy element content affects the formation of dust grains and molecules in the interstellar medium. It changes the cooling rates in collapsing gas clouds and the opacity in stellar atmospheres. For massive stars, the reduced abundance of iron group elements in particular weakens the line-driven component of stellar winds, which plays a central role in the mass loss history of stars that will become Wolf-Rayet objects. Thus, even before considering any specific star, the global properties of the Large Magellanic Cloud already impose distinctive boundary conditions on massive star evolution. Because the Large Magellanic Cloud is relatively nearby, and only modestly inclined to the line of sight, individual star-forming regions and clusters can be studied with high spatial resolution across a wide range of wavelengths, from radio to X-ray. High-resolution imaging with space-based observatories resolves the inner structure of clusters and the morphology of surrounding gas. Spectroscopy yields radial velocities, chemical abundances, and stellar parameters for large samples of stars. Infrared observations probe embedded star formation in dusty regions, while X-ray observations detect hot gas and energetic processes associated with massive stars and their remnants. Together, these datasets make the Large Magellanic Cloud an empirical foundation for models of massive star formation and feedback in low metallicity environments. Within this broader setting, the location of R136c can be described in purely structural terms. It resides in the inner disk of the Large Magellanic Cloud in a region where gas density radiation fields and stellar crowding are all high. It is a member of a very young massive cluster that lies in one of the principal star-forming complexes of the galaxy. The combination of low to moderate metallicity abundant gas and strong tidal influences has contributed to the creation of this cluster and others like it. To understand R136c as a hydrogen-rich Wolf-Rayet star, it is therefore necessary to view it first as one element in the broader stellar and interstellar structure of the Large Magellanic Cloud, whose global properties set the initial and boundary conditions for its formation and evolution. The Tarantula Nebula, also designated 30 Doradus, is the most prominent star-forming complex in the Large Magellanic Cloud, and provides the immediate galactic scale environment for the cluster that contains R136c. It lies in the northeastern part of the galaxy's disk and spans a physical size of roughly several hundred light-years, making it one of the largest known ionized hydrogen regions in the local universe. Its integrated luminosity and ionizing radiation is high enough that if the Tarantula Nebula were located at the distance of typical galactic star-forming regions, it would appear as one of the brightest nebulae in the sky. The nebula consists of ionized hydrogen gas traces of heavier elements and embedded star clusters at different evolutionary stages. Its high surface brightness and complex morphology make it a benchmark object for studying how massive stars interact with their natal environment in a low metallicity system. Optical imaging reveals a network of bright filaments, ridges and arcs, delineating regions where gas is compressed and ionized by young massive stars. Dark lanes of dust indicate colder, denser material that partially obscures the nebular emission along certain lines of sight. The brightest concentrations of emission trace the locations of the most intense ionizing sources, including the central cluster NGC 2070, but the nebula extends well beyond this core region and contains multiple secondary clusters and associations. Observations in narrow spectral bands, for example, centered on hydrogen recombination lines, or forbidden lines of oxygen and nitrogen map the ionization structure and gas density distribution across the complex. These maps show gradients in ionization state and electron density that reflect the combined influence of many massive stars and the inhomogeneous distribution of gas. Infrared observations penetrate the dust and reveal embedded young stellar objects and clusters that are not prominent in the optical. These sources mark sites where star formation is still ongoing within dense molecular clouds. The mid-infrared emission traces warm dust grains heated by ultraviolet radiation, while the far-infrared emission arises from cooler dust components that carry much of the reprocessed energy budget. Together with millimeter and radio observations of molecular lines, these data show that the Tarantula Nebula contains both ionized gas and significant reservoirs of molecular gas that fuel continued star formation. The coexistence of massive O-type stars evolved massive stars and deeply embedded protostellar objects indicates that star formation in 30 Doradus has proceeded over an extended interval and is not confined to a single burst. Spectroscopic studies provide quantitative information about the physical conditions in the nebula. Measurements of emission line ratios yield electron temperatures, electron densities and ionization parameters in different subregions. The typical electron temperatures are higher than in many Milky Way ionized hydrogen regions, consistent with the lower heavy element abundance of the Large Magellanic Cloud, which reduces cooling efficiency. Elemental abundances derived from nebular lines confirm that oxygen, nitrogen, and other heavy elements are present at subsolar levels. These results reinforce the view that the Tarantula Nebula is an important site for massive star formation and feedback under conditions that resemble those in star-forming galaxies at earlier cosmic epochs, where metallicities are lower than in the present-day Milky Way. The stellar content of the Tarantula Nebula is rich and diverse. In addition to the central massive cluster, there are numerous smaller clusters and loose associations of young stars distributed throughout the complex. Photometric surveys identify large populations of O and B-type stars, pre-main sequence stars, and intermediate mass stars at different evolutionary stages. The most massive stars concentrate in the central regions, while lower mass populations are more widely spread. This spatial segregation may reflect both the initial conditions of cluster formation and subsequent dynamical evolution. Age estimates indicate that while the central cluster is very young, with ages of only a few million years, some surrounding populations are older, indicating multiple episodes of star formation. Feedback from massive stars plays a central role in shaping the Tarantula Nebula. Ultraviolet radiation from hot stars ionizes surrounding gas, while stellar winds and in older subregions past supernova explosions inject mechanical energy. These processes create expanding shells, and bubbles drive shocks into the surrounding medium and can trigger or inhibit further star formation depending on local conditions. X-ray observations detect hot diffuse gas at temperatures of millions of degrees Celsius filling cavities carved by stellar winds and supernovae. Radio observations trace non-thermal emission in some regions, providing evidence for relativistic particles associated with shocks. The overall structure of the nebula is therefore the result of a balance between gravity, which draws gas into denser regions where stars can form, and feedback, which disperses or compresses gas in different zones. The Tarantula Nebula also serves as a key calibrator for models of starburst regions beyond the local group. Its integrated spectrum, if observed at the distance of faraway galaxies, would resemble that of a compact starburst region dominated by young, massive stars. By resolving individual stars and gas structures in 30, Doradus astronomers can test how well population synthesis and photoionization models reproduce the observed integrated properties. This comparison is essential for interpreting observations of distant galaxies where individual stars cannot be resolved and only integrated light is accessible. The Tarantula Nebula thus links local resolved studies of massive star formation to the broader context of galaxy evolution. Kinematic data add another layer of information. Measurements of gas velocities from emission line profiles reveal flows, expansions, and turbulence within the nebula. Some regions exhibit coherent expansion patterns consistent with bubbles driven by clusters, while others show complex velocity fields produced by overlapping feedback structures. Stellar radial velocities help to constrain the dynamics of clusters and associations embedded in the gas. Combined with estimates of gas mass and energy input from massive stars, these data allow an assessment of how efficiently feedback couples to the interstellar medium and whether the complex as a whole is gravitationally bound or dispersing. Within this environment, the central parts of the Tarantula Nebula host the most massive and luminous stars in the Large Magellanic Cloud, including those in NGC 2070 and its dense core R136. Although later sections will examine these clusters and R136c in detail, it is already clear at this stage that the extreme properties of the nebula, such as its high ionizing luminosity and mechanical energy input, are a direct consequence of the presence of numerous very massive stars. The Tarantula Nebula therefore defines the immediate star-forming context for R136c, setting the radiation field gas pressures and large-scale feedback conditions in which the star and its host cluster evolve. NGC 2070 is the central star cluster of the Tarantula Nebula and is the primary source of the ionizing radiation and stellar winds that sustain the nebula's high luminosity. It is embedded in the brightest part of the ionized gas complex and contains a high concentration of young, massive stars. The cluster extends over several tens of light years, with a dense central region and a more diffuse halo of young stars that blend into the surrounding stellar field of 30 Doradus. Photometric and spectroscopic surveys identify a large population of O-type and early B-type stars, as well as evolved massive stars such as Wolf-Rayet objects. The integrated luminosity of NGC 2070 is sufficient to account for most of the ionizing photon flux required to maintain the observed emission lines and surface brightness of the Tarantula Nebula, so the cluster is treated as the dominant power source of the complex. In terms of its physical parameters, NGC 2070 is classed as a young, massive cluster with stellar content density and total mass that resemble those inferred for protoglobular clusters in the early universe. Age estimates for NGC 2070 show that it is very young on stellar evolution timescales. Analyses of color magnitude diagrams and Hertzsprung-Russell diagrams constructed from resolved photometry of individual stars indicate that many of the most massive members have ages of only a few million years. The core region that includes the most luminous stars has an especially young characteristic age, while some populations in the outer parts of the cluster appear slightly older by a few million years. This age spread suggests that star formation in the NGC 2070 region has proceeded over an extended interval rather than as a single instantaneous burst. The presence of very massive stars that are still in the hydrogen burning phase, together with the small number of evolved massive stars and possible supernova remnants in the wider complex, indicates a sequence of star-forming episodes in and around the cluster that are closely spaced in time. The current configuration is therefore interpreted as a young system in which the most massive stars have only recently formed, but are already strongly affecting their surroundings. Estimates of the total stellar mass of NGC 2070 derived from star counts and integrated light modelling give values of the order of several 100,000 times the mass of the Sun, depending on the assumed initial mass function and the spatial boundaries adopted for the cluster. The stellar population spans a wide mass range from low-mass stars that are only detectable in deep imaging to very massive O-type stars whose initial masses are inferred to be at least around tens of times the mass of the Sun, and in some cases possibly exceeding 100 times the mass of the Sun. Correcting for incompleteness, crowding and extinction is essential when deriving these quantities, because the central regions are extremely dense and the faintest stars are difficult to detect. When these corrections are applied, the resulting mass and density place NGC 2070 firmly in the regime of young massive clusters that are compact-rich and potentially long-lived. The spatial structure of NGC 2070 is centrally concentrated but not uniform. High-resolution imaging with large ground-based telescopes and space-based observatories reveals a dense inner zone surrounded by a more extended distribution of stars. The stellar density peaks in the inner few light years where crowding is severe, and individual sources must be separated with advanced image processing techniques. Outside this inner region, the density decreases gradually and transitions into looser groupings and associations that still belong to the NGC 2070 system but are less compact. The core region, designated R136, sits near the center of this distribution and contains many of the most massive and luminous stars in the entire Tarantula Nebula. The outer parts of NGC 2070 host a mixture of massive and intermediate mass stars that generally show slightly older ages, consistent with the scenario in which multiple subclusters formed and subsequently merged or remained gravitationally bound within a common potential well. This internal structure indicates that NGC 2070 is not a simple single-component cluster, but a hierarchical system assembled from related star-forming events in the same gas complex. Multi-wavelength observations provide a detailed view of the stellar content and gas environment of NGC 2070. In the optical and ultraviolet imaging and spectroscopy, resolve individual massive stars, allowing determination of effective temperatures, surface, gravities, luminosities, and wind properties. Spectral classifications yield counts of O-type stars, early B-type stars, and Wolf-Rayet stars, which in turn constrain the ionizing photon output and mechanical energy injection from the cluster. Infrared observations penetrate dusty regions and reveal young stellar objects and pre-main sequence stars that are not prominent at shorter wavelengths, showing that lower mass star formation is also ongoing or has occurred recently in the vicinity of the cluster. X-ray imaging detects diffuse hot gas and point sources associated with massive stars colliding wind binaries and possible remnants of earlier supernova events. Radio observations trace ionized gas through free emission, and at longer wavelengths non-thermal emission from relativistic particles in shock fronts. The combination of these datasets shows that NGC 2070 is both a rich stellar system and a strong source of radiative and mechanical feedback. The ionizing radiation field generated by NGC 2070 plays a central role in setting the ionization state and thermal structure of the surrounding nebula. The large number of O-type stars in the cluster emits a high flux of photons with energies above the ionization threshold of hydrogen. This flux maintains the ionization of the extended gas in 30 Doradius and accounts for the strength of hydrogen recombination lines observed across the region. The cluster also contributes significantly to the ionization of helium and heavier elements affecting diagnostic line ratios that are used to infer physical conditions in the gas. Photoionization models that use empirically derived stellar populations for NGC 2070, combined with atmospheric models appropriate for the metallicity of the Large Magellanic Cloud, reproduce the observed nebula spectra reasonably well. These results support the conclusion that NGC 2070 dominates the ionizing photon budget of the Tarantula Nebula and can be used as a calibration point for interpreting unresolved starburst regions in more distant galaxies. Stellar winds from the massive stars in NGC 2070 supply an additional channel of feedback. Each massive star drives a supersonic wind with a terminal velocity of the order of thousands of kilometers per second and a mass loss rate that depends on its luminosity, temperature, and metallicity. Summed over the entire population of massive stars in the cluster, these winds inject a large amount of mechanical energy and momentum into the surrounding medium. The interaction between fast stellar winds and denser ambient gas produces shock fronts that heat gas to temperatures of millions of degrees Celsius observed as diffuse X-ray emission inside and around the cluster. Optical and radio images show shells and cavities where gas has been swept up by the expansion of hot shocked wind material. In some zones, these structures appear as roughly spherical bubbles. In others, they are elongated or irregular because they expand into an inhomogeneous medium. The net result is a complex pattern of cavities, filaments, and dense shells that influence where new stars can form and how gas is dispersed from the central regions. The internal dynamics of NGC 2070 are constrained by measurements of stellar radial velocities and, where available, proper motions. These data yield estimates of the velocity dispersion of the cluster from which a dynamical mass can be inferred under the assumption that the system is approximately in virial equilibrium. Comparisons between dynamical masses and photometric masses help to test assumptions about the initial mass function and about the degree of mass segregation within the cluster. Observations show that the most massive stars are strongly concentrated toward the center, indicating significant mass segregation. Given the young age of NGC 2070, this concentration may partially reflect primordial conditions in which massive stars formed, preferentially in dense regions, although dynamical processes can also operate on relatively short timescales in such a high-density environment. The resulting configuration has a deep central potential well, where very massive stars are located in close proximity. The high stellar density in the central parts of NGC 2070 increases the probability of close encounters and binary interactions among massive stars. Observations reveal a high fraction of spectroscopic binaries and systems with colliding winds, as indicated by radial velocity variations, composite spectra, and X-ray emission. These systems are important because binary evolution, mass transfer, and wind collisions can significantly modify the mass loss history, surface composition, and rotational properties of massive stars. In some cases, dynamical interactions in the dense core may lead to the hardening of existing binaries or even to stellar mergers. Such processes are considered when interpreting the observed properties of the most massive stars in the cluster, including those in the R136 core. They also have implications for the types of compact remnants and possible gravitational wave sources that might eventually form from this population. Viewed as a whole, NGC 2070 is the cluster-scale environment that sets the immediate stellar radiative and dynamical conditions for the inner core where R136c resides. Its large total stellar mass-rich population of very massive stars, strong ionizing radiation field, and intense mechanical feedback define the ambient background against which the properties of the core and its most extreme members must be understood. The core of NGC 2070, known as R136, is an exceptionally dense concentration of young massive stars, and forms the immediate cluster-scale environment around R136c. It occupies a region only a few light-years across, and yet contains a stellar population that in mass and luminosity rivals that of entire typical open clusters in the Milky Way. High-resolution imaging with large telescopes and space-based instruments is required to resolve individual stars in this core, because crowding is severe and many sources overlap along the line of sight. Even with such data, some of the brightest apparent sources are likely composites of multiple stars that cannot be fully separated at current angular resolution. This observational limitation means that estimates of the masses and luminosities of the most extreme members carry systematic uncertainties, but the overall picture of R136 as an extreme young cluster core is well established. The central stellar density in R136 is orders of magnitude higher than that in ordinary open clusters. Within a volume of a few cubic light-years, there are hundreds to thousands of stars, including dozens of very massive O-type and Wolf-Rayet stars. This high density has several consequences. It increases the frequency of close gravitational encounters and binary interactions among massive stars, influences the internal kinematics of the cluster, and enhances the collective radiative and mechanical feedback that the core delivers to its surroundings. The gravitational potential well created by this concentration of mass is deep, and the escape velocity from the innermost regions is high compared with that of looser clusters. As a result, R136 is expected to be gravitationally bound and dynamically complex, with long-term evolution that may differ from that of typical open clusters. The stellar content of R136 is dominated in terms of luminosity and feedback by very massive and hot stars. Spectroscopic classifications identify a large number of O-type stars of early spectral subtypes, with high effective temperatures and high ionizing photon output. In addition, there is a population of hydrogen-rich Wolf-Rayet stars of WN subtype, whose spectra show strong emission lines formed in dense stellar winds. These stars include some of the most luminous and massive known, with initial masses inferred to be at least around 100 times the mass of the Sun, and in some cases possibly significantly higher. The combined luminosity of these stars accounts for a substantial fraction of the ionizing radiation produced by NGC 2070 as a whole. Lower mass stars are also present in large numbers, but contribute less to the integrated ionizing output and mechanical energy, even though they dominate the total stellar mass by number. The age of the R136 core is very young, with most estimates placing it at only a few million years. This young age is inferred from the positions of its stars in color magnitude diagrams, from the presence of very massive hydrogen-burning stars, and from the absence of a large population of evolved post-main sequence massive stars. The narrow age range among the most massive members suggests that the core experienced a relatively brief and intense episode of star formation, even if surrounding regions show somewhat more extended histories. This brief formation interval, combined with the high density of gas in the progenitor cloud, likely contributed to the extreme properties of the cluster. In theoretical models of cluster formation, such conditions are associated with high star formation efficiencies and the production of very massive stars, making R136 an important empirical test of such models. The radiation field in the R136 core is extremely intense. Each very massive star emits a large flux of ultraviolet photons, and the cumulative effect of many such stars situated within a small volume produces a radiation energy density far exceeding that in ordinary star-forming regions. This field ionizes any residual gas in the core, and in its immediate surroundings raises the temperature of dust grains and affects the atmospheres and disk structures of lower mass stars that formed nearby. The hardness of the radiation spectrum determined by the high effective temperatures of the O-type, and Wolf-Rayet stars influences the ionization balance of helium and heavier elements in the gas, and therefore affects the nebular emission line spectrum observed toward the core. Models that synthesize the spectra of the observed stellar population are used to estimate the total ionizing photon output and to compare it with the requirements inferred from nebula diagnostics. Stellar winds from R136 stars add a mechanical component to this feedback. The very massive stars drive high-velocity dense winds that carry significant mass and kinetic energy away from the stellar surfaces. In a crowded core, these winds interact with each other as well as with any ambient gas forming shock fronts, where wind material is heated to high temperatures. Such colliding wind regions are sources of X-ray emission and can also create localized structures in the surrounding gas. On larger scales, the combined effect of many stellar winds contributes to the formation of hot low-density cavities and expanding shells that are visible in X-ray optical and radio observations. Quantifying this feedback requires summing over the individual mass loss rates and wind velocities of the massive stars and comparing the resulting mechanical luminosity with the gravitational binding energy and gas mass in the region. The internal kinematics of R136 reflect both the gravitational potential of the cluster and the influence of early dynamical processes, Observations of stellar radial velocities and where available proper motions reveal a velocity dispersion that is consistent with a massive compact cluster in approximate dynamical equilibrium. However, the presence of substructure and the possibility of ongoing relaxation and mass segregation mean that simple equilibrium models provide only a first approximation. The most massive stars are concentrated near the center, a configuration that can arise either because they formed preferentially in denser central regions, or because dynamical mass segregation has already had time to act. Given the young age of the core and the high stellar density, both factors may be relevant. Dynamical interactions in such an environment can lead to the hardening of binaries, the ejection of some stars as runaways, and in rare cases stellar mergers. These processes are considered in interpretations of the present-day mass function and the inferred initial masses of the most luminous stars. R136 is also an important analogue for extragalactic young massive clusters that cannot be resolved into individual stars. In distant starburst galaxies, clusters with similar masses and densities are observed only as compact luminous sources whose integrated light is dominated by massive stars. By resolving R136 and determining its stellar content and structure in detail, astronomers can test and calibrate population synthesis models that aim to infer cluster properties from unresolved observations. Comparisons of these models with the actual census of stars in R136 help to identify uncertainties in stellar evolution models, particularly at the highest masses, and to refine predictions for ionizing spectra and feedback outputs in star-forming galaxies across cosmic time. From the perspective of R136c, the core provides the cluster-scale environment that defines the local stellar density radiation field and dynamical conditions. R136c is one of several very massive and luminous stars in this core, and its observed properties must be interpreted against the background of the broader massive star population. The presence of numerous neighbouring massive stars means that some observational diagnostics such as nebula emission and diffuse X-ray emission reflect the combined influence of many sources rather than that of a single object. At the same time, the extreme conditions in the core, including high stellar densities and strong winds, shape the immediate surroundings of each massive star in ways that differ from those in more isolated environments. Understanding the R136 core is therefore a necessary step before focusing specifically on the location, classification, and local environment of R136c itself. Within the dense core of R136, R136c is identified as one of the most luminous and massive stellar systems, and its characterization relies on a combination of high-resolution imaging and detailed spectroscopy. It is located in the central region of the core where stellar crowding is severe, and the local projected density of bright stars is very high. Early ground-based observations could not clearly separate individual sources in this area, so R136c and its neighbours were originally treated as blended components of a compact luminous knot. The deployment of space-based imaging with sufficient angular resolution allowed astronomers to resolve this knot into multiple bright stars, and to assign separate designations to the most prominent objects, including R136a components, R136b and R136c. Even with these data, the angular separations among the brightest members remain small, and photometric measurements must account for overlapping point spread functions and background light from numerous fainter stars in the field. Photometry of R136c in optical and near-infrared bands shows that it ranks among the brightest individual sources in the core, with apparent magnitudes comparable to those of the other very luminous members. Transforming these observed fluxes into intrinsic luminosities requires corrections for interstellar extinction distance and contamination by nearby sources. The extinction in the direction of the Tarantula Nebula is moderate but not negligible, and it can vary on small spatial scales because of dust structures in the nebula. Multi-band photometry and spectroscopy are used together to estimate the color excess and to apply an appropriate extinction law for the Large Magellanic Cloud. Once these corrections are applied, R136c is inferred to have a luminosity of several million times the luminosity of the Sun, with uncertainties arising from the adopted extinction distance modulus and model atmosphere parameters. These luminosity estimates place R136c firmly in the regime of the most luminous known stars and motivate the interpretation that it is an extremely massive object. Spectroscopic observations provide the main basis for classifying R136c and for constraining its physical parameters. High signal-to-noise spectra obtained at optical and ultraviolet wavelengths show strong broad emission lines of helium and nitrogen, together with weaker features from other ions. The line profiles and relative strengths correspond to those of hydrogen, rich Wolf-Rayet stars of nitrogen sequence, often labelled as Duduen subtype, with clear evidence that hydrogen is still present in the atmosphere. The presence of hydrogen lines in emission distinguishes these objects from classical hydrogen-free Wolf-Rayet stars, while the strong nitrogen lines indicate that material processed by the carbon-nitrogen-oxygen cycle is present near the surface. Line profile modelling using non-local thermodynamic equilibrium atmosphere codes yields estimates of the effective temperature mass loss rate and wind terminal velocity. The inferred effective temperature is very high, consistent with a hot compact star that emits a large flux of ionizing photons. The strong broad emission lines indicate a dense high-velocity wind, and their detailed shapes and equivalent widths are used to constrain the wind structure. To derive a mass estimate for R136c, observers combine the inferred luminosity and effective temperature with theoretical evolutionary tracks for very massive stars at the metallicity of the Large Magellanic Cloud. For hydrogen-burning stars in this part of the Hertzsprung-Russell diagram, the relation between luminosity and mass is steep, so small changes in luminosity correspond to significant differences in mass. Models that match the observed luminosity and temperature of R136c suggest present-day masses of at least around 100 times the mass of the Sun, and possibly more than 200 times the mass of the Sun. These values depend on assumptions about rotation, mass loss history, and internal mixing, and they are affected by uncertainties in the luminosity. As a result, published estimates span a range, but they converge on the conclusion that R136c is an extremely massive star. The fact that several other stars in R136, such as some of the R136a components, occupy similar regions of the Hertzsprung-Russell diagram reinforces the view that the core hosts a population of stars near or beyond the upper mass range, commonly inferred for field stars in the Milky Way. The possibility that R136c is not a single star but a close binary system introduces additional complexity into its interpretation. Some spectroscopic and X-ray observations suggest that at least a fraction of the very luminous WN stars in R136, potentially including R136c, may be colliding wind binaries. In such systems, two massive stars in a close orbit each drive strong stellar winds, and the collision of these winds produces shock-heated gas that emits X-rays and affects the profiles of some spectral lines. If R136c is a binary, the luminosity inferred from unresolved photometry would represent the combined output of the two components, and the individual stellar masses would be lower than the single star estimate, although still very high. Radial velocity monitoring and spectral line profile analysis are used to search for periodic variability indicative of orbital motion, but the crowded environment and limited temporal sampling make it difficult to obtain definitive constraints. As a result, the binary status of R136c remains an open question in current work, and both single-star and binary interpretations are considered when comparing observations with evolutionary models. Astrometric measurements and high-resolution imaging also help to characterize the immediate vicinity of R136c. Several nearby stars lie within fractions of an arcsecond, corresponding to projected separations of a fraction of a light-year at the distance of the Large Magellanic Cloud. These neighbors contribute background light and can bias photometry if not properly accounted for. Deconvolution techniques and point spread function fitting are applied to separate the flux contributions of R136c and adjacent sources. In some filters, unresolved blends remain a source of uncertainty, especially in the most crowded central regions. Nevertheless, the combination of photometric, spectroscopic, and imaging data provides a consistent picture in which R136c is one of the dominant luminous sources in the core. In comparative studies of the most massive stars in R136, R136c is often listed alongside other luminous WN stars such as R136a1, R136a2, and R136r3. These objects share similar spectral characteristics and occupy overlapping regions in the luminosity temperature plane. Differences in line strengths, wind properties, and derived parameters reflect both intrinsic variations and the impact of modeling assumptions. R136c does not stand out as uniquely extreme in every respect, but it is representative of the upper end of the mass and luminosity distribution in the core. From the standpoint of cluster properties, it is one member of a small group of stars that together dominate the ionizing radiation field and mechanical energy injection in the central region. From the standpoint of stellar physics, it provides one of several test cases for models of very massive star structure winds and evolution at low metallicity. Overall, R136c is identified and characterized through a careful synthesis of resolved imaging, multi-wavelength photometry, and detailed spectroscopy in a challenging crowded environment. Its location near the center of R136, its high luminosity after correction for extinction, and blending its hydrogen-rich Wolf-Rayet spectrum, and its placement on theoretical evolutionary tracks, all support the conclusion that it is an extremely massive, very luminous star or binary system. The remaining uncertainties about its exact mass, wind properties, and possible multiplicity do not alter this basic classification, but are important for refining models of very massive stars and for understanding how such objects contribute to the energy budget and chemical evolution of their host clusters. On the scale of the central regions of NGC 2070, the combined output of all massive stars in and around R136 constitutes a major source of feedback on the surrounding interstellar medium. In this context, feedback refers to the way in which radiation stellar winds and where present supernova explosions from stars return energy and momentum to the gas from which they formed. In the environment of R136, the dominant contributors at the present epoch are the ultraviolet radiation fields and supersonic winds of O-type stars and hydrogen-rich Wolf-Rayet stars among them. R136c. These processes set the ionization state temperature, density, structure, and kinematics of the gas within several tens of light-years of the core and influence how gas is retained, compressed, or dispersed in the vicinity of the cluster. Radiative feedback is most directly traced by the ionized hydrogen surrounding the core. The massive stars in R136 emit large numbers of photons with energies above the ionization threshold of hydrogen. These photons are absorbed by neutral hydrogen atoms in the surrounding gas, producing ionized regions in which the electrons and protons recombine and emit characteristic spectral lines. The volume over which the gas remains ionized is determined by the balance between the rate of ionizing photons and the recombination rate, which depends on electron density and temperature. Observations of hydrogen recombination lines and forbidden lines of heavier elements in the central parts of the Tarantula Nebula indicate that electron densities near the cluster are relatively high, while electron temperatures are elevated compared with many Milky Way ionized regions because of the lower heavy element abundance. The radiation energy density near R136 is correspondingly high, and any neutral gas that enters this zone is rapidly ionized. This feedback reduces the amount of cold dense gas in the immediate surroundings of the core and contributes to clearing a cavity in the original natal cloud. Mechanical feedback from stellar winds provides an additional means of coupling stellar energy to the gas. Each massive star in R136 drives a fast stellar wind with a terminal velocity of the order of thousands of kilometers per second, and a mass loss rate that, when integrated over time, can remove a non-negligible fraction of the stellar envelope. In the dense core environment, these winds interact with each other and with any residual gas. Where winds from different stars collide, shock fronts form and heat gas to temperatures of millions of degrees Celsius, producing diffuse X-ray emission. Where winds encounter denser gas clumps or filaments, they sweep up material into shells and compressed layers. Hydrodynamic models of such regions predict the formation of a hot low-density interior cavity, surrounded by a shell of swept-up material, and observations around R136 identify structures consistent with this picture, although the real three-dimensional geometry is complex and affected by inhomogeneities in the ambient medium. On larger scales, the combined winds from all massive stars in NGC 2070, including those in R136, drive expanding bubbles and superbubbles that are visible in optical and X-ray maps. In the immediate region around R136, the gas distribution shows a central area with relatively low emission measure, interpreted as a cavity with reduced gas density, surrounded by brighter arcs and filaments. These arcs trace zones where gas has been compressed by the action of winds and radiation pressure. Spectroscopic measurements of line widths and Doppler shifts across these features reveal velocity gradients and expansion patterns of a few tens of kilometers per second, consistent with the kinetic energy input expected from the cluster population. The gas in these shells is denser and cooler than the interior hot gas, but still ionized by the pervasive radiation field. Beyond the radius where the influence of R136 alone dominates feedback from other clusters and associations, in 30 Doradus overlaps, creating a network of interacting structures. The density and pressure structure of the gas near R136 can be quantified by combining emission line diagnostics with models of photoionized gas. Line ratios sensitive to electron density indicate values that can reach into the thousands of particles per cubic centimeter in some compressed ridges, while more diffuse zones have densities lower by an order of magnitude or more. The thermal pressure in the ionized gas reflects both the density and the elevated temperature set by the balance of heating and cooling processes. Radiation pressure also contributes, especially very close to the most luminous stars, where the momentum carried by photons can be comparable to or exceed the gas pressure. The relative importance of these components varies with distance from the core and with local gas distribution. In regions shadowed from direct stellar light, gas can recombine and cool, forming neutral or molecular clouds at the edges of the ionized structures. These clouds can be sites of ongoing or future star formation, influenced by the external pressure, exerted by the surrounding ionized gas and hot wind bubble. In addition to winds and radiation, the broader NGC 2070 region has likely experienced some supernova activity, particularly in its outer parts, where slightly older, massive stars reside. Supernova remnants in the wider Tarantula Nebula complex provide evidence that massive stars have already completed their evolution and exploded in the past few million years. The contribution of such events specifically to the present environment immediately around R136 is less certain, because the core itself is so young that most of its very massive stars are still in the hydrogen burning phase. Nevertheless, on scales of tens of light years, shock waves from previous supernovae can intersect with wind-driven shells and ionized cavities, further complicating the gas kinematics and structure. X-ray observations of diffuse emission around NGC 2070 and R136 detect hot gas whose total energy content exceeds what winds alone from the current stellar population would supply over their lifetimes, a result that suggests an additional contribution from past supernovae in the region. Kinematic studies based on emission line profiles map the velocity field of the gas within and around the R136 core. These data reveal both ordered motions such as expansion of shells and disordered motions interpreted as turbulence driven by the overlapping influence of multiple energy sources. The typical non-thermal line widths exceed those expected from purely thermal broadening, at the measured temperatures indicating a substantial turbulent component. Estimates of the turbulent kinetic energy density can be compared with the energy injection rates from winds and radiation-driven flows, providing a check on the consistency of feedback models. The momentum carried by bulk flows in shells and bubbles is another diagnostic. Integrating the mass of gas involved in the motions and multiplying by the observed expansion velocities yields momentum budgets that can be related to the cumulative contribution of stellar winds and radiation pressure, including contributions from stars like R136c. The feedback from R136 and its surroundings also affects the gravitational state of gas in the central region. Gas that is heated to high temperatures and accelerated to high velocities can escape the immediate gravitational potential of the cluster and of the Large Magellanic Cloud disk, contributing to an outflow on larger scales. Gas that is compressed into dense layers at the edges of bubbles may become gravitationally unstable and fragment into new star-forming cores. The efficiency with which gas is removed from the inner region versus recycled into new stars determines whether the system will retain enough gas to sustain further cluster formation or will evolve toward a gas-poor state dominated by existing stars. In the vicinity of R136, observations show that much of the original natal gas has been cleared from the central few light years, leaving a stellar-dominated core. At somewhat larger radii, molecular and neutral gas clouds remain, although they show clear signatures of perturbation by feedback. From the specific perspective of R136c, the key point on this scale is that the star does not exist in isolation, but as part of a compact system in which radiation fields, hot gas, and dynamic structures are all shaped by the cumulative effect of many massive stars. Any gas that lies close to R136c is embedded in a medium that has already been heated, ionized, and mechanically disturbed by cluster-scale feedback. The local density, temperature, and ionization state of this gas must be interpreted within this broader context when analyzing observations of emission or absorption features associated with the immediate environment of the star. The gas immediately surrounding R136c is part of the ionized component of the Tarantula Nebula, but shows conditions that reflect the proximity to an extremely luminous hot star embedded in a dense cluster core. On scales of a fraction of a light year to a few light years, the local medium consists primarily of ionized hydrogen, with contributions from ionized helium and heavier elements. The gas is exposed to a strong ultraviolet radiation field, produced both by R136c and by neighboring massive stars in R136, so the ionization fraction is high, and the temperature remains near the characteristic values for photoionized regions in low metallicity environments. In this zone, gas dynamics and thermal structure are controlled by the balance between radiative heating, radiative and collisional cooling, and mechanical perturbations from stellar winds and cluster scale flows. Because R136c lies in the central part of the core, any neutral or weakly ionized material close to the star is rapidly ionized, and residual dense clumps are confined to small shielded regions, where the radiation field is attenuated by intervening gas and dust. Observationally, the immediate environment of R136c is studied through high-resolution imaging and spectroscopy in emission lines that trace ionized gas. Narrowband images centered on hydrogen recombination lines and on forbidden lines of oxygen and nitrogen show bright filamentary structures and diffuse emission projected against the stellar background of R136. Within the angular resolution limit, the emission near R136c does not break up into a single simple shell, but shows a complex morphology influenced by overlapping contributions from many massive stars. Nevertheless, analysis of line strengths and surface brightness profiles as a function of projected distance from R136c provides information about how strongly the star contributes to local ionization compared with the cluster as a whole. Regions immediately adjacent to the star exhibit high excitation conditions, indicated by relatively strong emission from higher ionization stages of oxygen and other elements. This pattern is consistent with a very hard radiation field produced by hot luminous stars of O-type and Wolf-Rayet type, including R136c. Physical conditions in the local gas can be quantified using standard nebula diagnostics. Ratios of temperature-sensitive emission lines yield electron temperatures that are elevated relative to solar metallicity, ionized regions reflecting reduced cooling efficiency in the Large Magellanic Cloud. Electron densities inferred from density-sensitive line ratios span a range with values in compressed filaments, and ridges reaching thousands of particles per cubic centimeter, while more diffuse components in the same line of sight show densities lower by an order of magnitude or more. The resulting pressure structure is correspondingly inhomogeneous. Close to R136c, the combination of high density in some zones and high temperature in all ionized gas produces thermal pressures that exceed those in more distant nebular regions. This pressure difference contributes to gas flows away from the core and to the shaping of small-scale structures such as bright edges and arcs. The radiation field near R136c is characterized not only by its intensity, but also by its spectral hardness. The ionization parameter defined as the ratio of ionizing photon density to gas density is high in the inner parts of R136 and declines with increasing distance from the core. Spectroscopic measurements of line ratios involving successive ionization stages of the same element provide empirical constraints on this parameter. Close to R136c, high ionization lines are strong, indicating that the local ionization parameter is large. Photoionization models that incorporate the combined spectra of the massive stars in R136, adjusted to match the metallicity of the Large Magellanic Cloud, reproduce the observed line ratios reasonably well and show that stars with very high effective temperatures, including R136c, are required to account for the hardest part of the radiation field. in the immediate vicinity of the stardust grains mixed with the gas are exposed to strong ultraviolet and optical radiation, leading to heating and in some cases destruction of smaller grains. Infrared observations show warm dust emission near the core, but suggest that the dust content is reduced close to the most luminous stars compared with more distant shielded regions. Kinematic information from emission line profiles reveals the motion of gas near R136c in both ordered and disordered components. Spectra obtained with integral field units, or narrow long slits across the core showline, broadening in excess of thermal values, indicating significant non-thermal motions. These broadened profiles are interpreted as a combination of turbulent motions and bulk flows driven by the combined feedback from stellar winds and radiation. In some positions, line centroids are shifted relative to the systemic velocity of the cluster, implying net flows of gas along the line of sight. These shifts can represent expansion of small local shells streaming motions along filaments, or the influence of larger-scale bubbles centered on the cluster. Because multiple structures overlap in projection, it is not always possible to associate a given velocity component uniquely with the influence of R136c, but the overall picture is that the gas near the star is kinematically active rather than static. The magnitude of these motions, typically of the order of several tens of kilometers per second, is consistent with expectations for gas that has been accelerated by radiation pressure and wind-driven shocks in a dense cluster core. Small-scale variations in density and ionization state around R136c likely arise from the interaction between the strong radiation field and an initially inhomogeneous gas distribution. Dense clumps and filaments embedded in a lower density medium can survive near the core if their internal pressures are high enough to resist rapid dispersal, and if they are partially shielded from direct radiation by surrounding gas. Their irradiated surfaces become bright ionization fronts emitting strongly in recombination and forbidden lines. Behind these fronts toward the star gas is fully ionized and heated, while deeper inside the clumps where radiation is attenuated, gas can remain neutral or molecular. The exact distribution of such structures near R136c is difficult to reconstruct because of projection effects and the limitations of angular resolution, but the presence of sharp brightness gradients and localized peaks in emission line maps indicates that significant small-scale structure exists even in the central regions. Over time, these clumps are subject to photoevaporation, in which ionized gas flows off the illuminated surfaces into the surrounding medium, altering both the clumps and the ambient gas. The immediate ionized environment of R136c also influences and is influenced by the star's own outflow and radiation-driven processes, although the detailed structure of the stellar wind itself is treated separately. Gas very close to the star is part of a flow that transitions from the dense stellar atmosphere into the surrounding nebula. Beyond the region where the wind accelerates, the outflow interacts with the ambient ionized medium. The local density and pressure of that medium set boundary conditions for the formation of wind termination shocks and contact discontinuities between wind material and pre-existing gas. Observational signatures of these interactions in the immediate vicinity of R136c are difficult to isolate from those of neighboring massive stars, but they contribute to the small-scale variations in emission measure and temperature seen around the core. In this sense, the gas near R136c is both a product of cluster-scale feedback and a local environment that responds directly to the luminosity and mass loss of the star. In summary, the local ionized gas around R136c is a high-excitation, high-pressure component of the Tarantula Nebula that reflects the combined influence of an intense radiation field, dense stellar winds and an inhomogeneous initial gas distribution. Its temperatures, densities, ionization state, and kinematics can be inferred from nebula diagnostics and provide important constraints on models of feedback in dense cluster cores. This environment forms the immediate external medium into which the outer wind and atmosphere of R136c expand and within which observational signatures of the star's energy output must be interpreted. R136c is classified as a hydrogen-rich Wolf-Rayet star of the nitrogen sequence, and is usually assigned to an early WN subtype. A Wolf-Rayet star is defined observationally by a spectrum dominated by broad emission lines, rather than the absorption lines that characterize most hot stars. In the nitrogen sequence labeled WN, the strongest emission lines arise from helium and nitrogen ions, while in the carbon sequence labeled WC carbon and oxygen lines dominate. The spectrum of R136c shows strong emission from helium and nitrogen, together with clear evidence for hydrogen, placing it among the WN stars that retain a significant hydrogen component in their outer layers. This classification indicates that R136c is both very hot and strongly mass-losing, with an extended expanding atmosphere in which emission lines form. At the same time, the presence of hydrogen suggests that it is in an early evolutionary phase compared with classical hydrogen-free Wolf-Rayet stars, consistent with its membership in a very young cluster core. The observed spectrum of R136c has been recorded at optical and ultraviolet wavelengths with medium and high spectral resolution. In the optical region, it exhibits broad emission features of singly ionized and doubly ionized helium, as well as lines of nitrogen in multiple ionization stages. Hydrogen Balmer lines are present but are blended with helium features, so careful modeling is required to separate their contributions. In the ultraviolet, additional lines from highly ionized species appear reflecting the hard radiation field of a very hot star and the ionization structure of its wind. The emission lines are significantly broader than thermal line widths, with full widths at half maximum, corresponding to velocities of the order expected for supersonic outflows. The continuum is bright and relatively smooth, providing a background against which the emission lines are superposed. Compared with ordinary O-type supergiants in the same cluster, 136c shows much stronger and broader emission, confirming that its outer layers differ qualitatively from those of stars with more conventional photospheric spectra. The emission line spectrum of R136c arises in an extended expanding atmosphere that functions as a dense stellar wind. In such an atmosphere, the concept of a single sharp photosphere is replaced by a region of finite radial extent, where the optical depth in the continuum transitions from high to low values. Photons generated in the deeper layers interact with moving material as they propagate outward, and recombination and scattering processes in the wind produce the observed emission lines. The Doppler broadening is dominated by bulk wind motions rather than by thermal speeds. Line formation calculations for such stars must account for non-local thermodynamic equilibrium conditions, because the densities are low enough and the radiation field is strong enough that level populations do not follow simple thermal distributions. In models tailored to R136c, the wind is treated as spherically symmetric and steadily expanding with a prescribed velocity law and density profile linked through mass continuity. Radiative transfer is solved in this moving medium to match the observed line profiles and strengths. Quantitative analysis of the spectrum of R136c uses non-local thermodynamic equilibrium atmosphere codes that combine radiative transfer statistical equilibrium and hydrodynamic constraints in a consistent framework. Input parameters include the stellar luminosity, a characteristic temperature at a reference radius in the atmosphere, the mass loss rate, the velocity law of the wind, the degree of small-scale clumping, and the chemical abundances of hydrogen, helium, nitrogen, and other elements. The metallicity is set to values appropriate for the Large Magellanic Cloud. By adjusting these parameters until the synthetic spectrum reproduces the observed continuum slope and emission line strengths, one obtains estimates of the effective temperature, the radius at which the Rosseland optical depth has a specified value, the mass loss rate, and the wind terminal velocity. For R136c, such models yield effective temperatures in the range typical of early WN stars, indicating a very hot atmosphere that emits strongly in the extreme ultraviolet. The luminosity derived from the models, when combined with the known distance to the Large Magellanic Cloud and the adopted extinction, agrees with independent luminosity estimates from photometry. The hydrogen-rich nature of R136c is established through detailed inspection of line blends that involve hydrogen and helium series. In WN stars, the so-called Pickering series of helium can be used to assess hydrogen content because certain helium transitions fall close to hydrogen-Balmer lines. If hydrogen is absent, the strengths of these helium lines follow predictable patterns. If hydrogen is present, additional opacity and emission modify the profiles. In R136c, the observed pattern requires a non-zero hydrogen abundance in the atmosphere. Model fits indicate hydrogen mass fractions that are significantly lower than in unevolved solar composition stars, but still substantial. The nitrogen lines are strong and reflect enhanced nitrogen abundance at the surface, a signature of material that has undergone carbon-nitrogen-oxygen cycle processing. Thus, the spectrum shows both processed material and residual hydrogen. This combination is characteristic of very massive stars that are still burning hydrogen in their cores, but have experienced strong mixing and mass loss that expose CNO-processed layers at the surface. The early WN subtype assigned to R136c is based on the relative strength of nitrogen lines in different ionization stages and on the overall ionization level of the spectrum. In this scheme, earlier subtypes correspond to higher ionization, and R136c falls among the early types, consistent with its high effective temperature. The classification is refined by comparing line ratios such as those of nitrogen-4 to nitrogen-3, as well as helium-2 line strengths. Hydrogen-rich WN stars of this kind are sometimes described as WNH types, to highlight the presence of hydrogen. In the R136 core, several very luminous stars are classified as WNH objects, and R136c is one of them. While the classification system is observational and does not directly specify mass or evolutionary stage, it provides a practical framework for comparing stars of similar spectral characteristics and for selecting appropriate atmosphere and evolutionary models. From the point of view of stellar evolution, the designation of R136c as a hydrogen-rich WN star at very high luminosity implies that it is in a phase often identified with very massive core hydrogen-burning stars that have entered a Wolf-Rayet spectral regime early in their lives because of their strong mass loss and internal mixing. Evolutionary tracks computed for very massive stars at Large Magellanic Cloud metallicity predict such phases in which stars retain a significant fraction of their hydrogen, while their surfaces show signatures of CNO-processed material. The connection between these models and the observations of R136c is made by comparing the positions of the star in the luminosity temperature plane with the theoretical tracks, and by matching the observed surface abundances with model predictions at particular evolutionary times. Within the uncertainties of both models and data, 136c appears consistent with a very young very massive star that has already lost part of its initial mass, but remains in the hydrogen-burning stage. The classification of R136c as a hydrogen-rich WN star also has direct implications for its role as a source of ionizing photons and mechanical energy in the cluster. Its high effective temperature means that it emits a large flux of photons capable of ionizing hydrogen and helium. Its dense wind required to produce the observed emission lines carries a substantial mass loss rate and momentum flux. In cluster scale, photoionization and feedback models, stars of this type are assigned prominent roles in maintaining the ionization of surrounding gas and in powering wind-driven structures. For R136c, the spectroscopic classification combined with quantitative atmosphere modeling therefore provides the primary observational basis for treating it as an extremely luminous hot mass losing star embedded in the R136 core. These outer atmospheric properties define the boundary conditions for the more detailed description of the wind, the extended atmosphere and the underlying envelope and interior. The stellar wind of R136c is a continuous radiation-driven outflow that carries mass momentum and energy away from the star at high speed. As a hydrogen-rich Wolf-Rayet star of the nitrogen sequence R136c has a wind that is denser and more extended than the winds of most O-type stars, and the properties of this wind are central to understanding both the observed spectrum and the influence of the star on its surroundings. In observational terms, the wind is inferred from the presence of broad emission lines electron-scattering wings, and in the ultraviolet P-Cygni profiles in resonance lines, all of which indicate a supersonic expanding atmosphere with large optical depths in key transitions. Theoretical models identify the wind as being driven mainly by the transfer of momentum from the star's intense radiation field to the atmospheric gas through absorption and scattering in metal lines, a mechanism often referred to as line-driven acceleration. Because R136c is extremely luminous, with a luminosity of several million times the luminosity of the Sun, the radiative flux at its surface is high enough that the outward force exerted on the gas by radiation can overcome gravity and launch a powerful wind. The terminal velocity of the wind is constrained by the observed widths of emission lines and by the absorption troughs of ultraviolet P-Cygni profiles. In R136c, these diagnostics indicate velocities of the order of thousands of kilometers per second comparable to other early WN stars at similar metallicity. The wind accelerates from near the local sound speed at the base of the atmosphere to this terminal velocity over a radial range that is small compared with the overall extent of the nebula, but large compared with the underlying stellar radius. The acceleration is often described by a parameterized velocity law in which the speed increases monotonically with radius. The precise shape of this velocity law affects line formation because emission lines sample different parts of the wind and therefore different ranges of velocity and density. By fitting synthetic line profiles to the observations, modelers can constrain both the terminal velocity and the approximate acceleration profile. The broad wings of some emission lines are shaped not only by the bulk outflow, but also by electron scattering, which redistributes photons in frequency and provides an additional probe of the column density of free electrons in the wind. Mass loss rates for R136c are derived from diagnostics that depend on the density of the wind. Because emission in recombination lines and free continuum scales with the square of the density, the strengths of these features are sensitive to the amount of material in the outflow. In practice, atmosphere models that include non-local thermodynamic equilibrium effects are used to match simultaneously the continuum shape and the emission line strengths, yielding a mass loss rate that reproduces the observed fluxes. Radio and infrared observations can offer independent constraints, because free emission from an ionized wind produces a characteristic spectral slope and flux level that depend on the mass loss rate and wind velocity. For R136c, the derived mass loss rates are large, typical of very luminous Wolf-Rayet stars, and imply that over the timescale of core hydrogen burning, the star can shed a non-negligible fraction of its initial mass through wind-driven outflow alone. The exact value depends on the adopted clumping factor in the wind, because small-scale inhomogeneities increase the emission at fixed average mass loss rate. Clumping in the wind of R136c is an important consideration in quantitative analysis. Observations of Wolf-Rayet stars, including those in R136, indicate that their winds are not smooth, but structured on small scales, with density enhancements and rarefied regions. This structure is thought to arise from instabilities inherent to line-driven winds and from additional perturbations near the base of the atmosphere. If clumping is not taken into account, mass loss rates inferred from density-squared diagnostics can be overestimated because a clumped wind produces more emission for the same average mass flux. Atmosphere models therefore introduce a clumping factor, sometimes as a function of radius to account for this effect. For R136c, the adoption of realistic clumping factors reduces the mass loss rate compared with smooth wind assumptions, but leaves it firmly in the high-range characteristic of very massive luminous Wolf-Rayet stars. Clumping also affects the ionization balance in the wind because denser clumps can recombine more efficiently, altering line strengths in ways that must be reproduced by the models. Metallicity plays a key role in setting the wind properties of R136c because the line-driven mechanism depends on the presence of metal ions that provide opacity in the ultraviolet. The Large Magellanic Cloud has a lower heavy element abundance than the solar neighborhood, and this reduces the number of metal lines available to transfer momentum from photons to gas. For stars of a given luminosity and effective temperature, theoretical prescriptions predict that mass loss rates scale with metallicity in a way that reduces the wind strength at lower metallicity. In R136c, however, the extremely high luminosity compensates for this effect to a significant extent, and the mass loss rate remains high. Comparisons between atmosphere models tailored to Large Magellanic Cloud metallicity and those for solar metallicity analogues suggest that while the wind of R136c may be somewhat weaker than that of a comparable star in a galaxy, with higher metallicity, it still lies in the regime where radiation pressure is close to balancing gravity in the outer layers. This near balance is reflected in the high Eddington factor, inferred for the star, which measures the ratio of radiative to gravitational force and provides a convenient way to understand why the wind is so easily launched. The momentum and kinetic energy carried by the wind of 136c can be expressed in terms of its mechanical luminosity, which is the rate at which kinetic energy is transported away from the star. This quantity is given by 1/2 of the mass loss rate multiplied by the square of the terminal velocity, and for R136c it reaches values that are a significant fraction of the radiant energy output in absolute terms, even though the radiative luminosity remains dominant. The wind momentum flux given by the mass loss rate multiplied by the terminal velocity can also be compared with the momentum available from the radiation field, namely the stellar luminosity divided by the speed of light. The ratio of these quantities, often termed the wind efficiency, provides a test of wind driving theory. In many Wolf-Rayet stars, including those in low metallicity environments, this ratio exceeds unity, indicating that multiple scattering of photons in the wind allows the transfer of more momentum than a single scattering limit would permit. For R136c, the high luminosity and dense wind likely produce a wind efficiency that is consistent with these expectations, reinforcing the interpretation of a multi-scattered line-driven flow. If R136c is part of a colliding wind binary system, as some observations suggest for a subset of the very luminous WN stars in R136, its wind properties have additional observable consequences. In such a system, the winds from the two massive stars meet in a region where the ram pressures balance, forming a contact discontinuity and a pair of shocks. Gas passing through these shocks is heated to very high temperatures and can emit strongly in X-rays. The luminosity and spectrum of this emission depend on the mass loss rates, velocities, and separation of the stars. High-resolution X-ray observations of the R136 core detect point-like and diffuse emission that may include contributions from colliding wind binaries. In the case of R136c, the presence of enhanced X-ray emission or peculiar line profiles could signal such an interaction, although crowding and the combined influence of many nearby stars complicate the interpretation. If a colliding wind region is present, it provides an additional diagnostic of wind parameters because the shape and location of the interaction zone depend on the ratio of wind momentaire of the two components. The wind of R136c not only affects the local gas but also plays a central role in the star's own evolution by removing mass and angular momentum from the outer layers. Over the timescale of core hydrogen burning, sustained high mass loss can significantly reduce the star's mass, alter its surface composition, and change its internal structure. Material lost in the wind is enriched in helium and nitrogen, reflecting the exposure of CNO processed layers, and thus contributes to the chemical enrichment of the surrounding medium. The removal of angular momentum through the wind can slow the rotation of the outer layers, potentially reducing the efficiency of rotation, induced mixing compared with an otherwise similar star with weaker mass loss. Evolutionary models for very massive stars at Large Magellanic Cloud metallicity incorporate prescriptions for wind mass loss and show that the integrated effect of such winds is crucial in determining whether the star will evolve into a more classical hydrogen poor Wolf-Rayet phase before core hydrogen exhaustion, or will retain a significant hydrogen envelope for a longer time. For R136c, the inferred mass loss rate places it in a regime where wind-driven mass loss is expected to be one of the dominant influences on its subsequent evolution. On the scale of the R136 core and the central Tarantula Nebula, the wind of R136c is one contribution among many from massive stars, but its magnitude and composition make it an important component of the overall feedback budget. The outflow carries energy momentum and processed material into the ionized gas immediately surrounding the star, and ultimately into the larger interstellar medium of the cluster and nebula. In this way, the detailed wind properties derived from spectroscopy and atmosphere modeling of 136c are not only parameters of a single star, but also inputs to cluster scale and nebula scale models that aim to reproduce the observed structure and emission of one of the most active star-forming regions in the local group. The description of the wind as a dense radiation-driven outflow with high terminal velocity and high mass loss rate therefore provides the physical link between the stellar atmosphere of R136c and the extended atmosphere and effective photosphere region that will be examined next. The outer envelope and effective photosphere of R136c form the interface between the dense radiation-driven wind and the deeper quasi-hydrostatic layers of the star. In this regime, the structure is no longer well described by the simple notion of a sharp stellar surface, as used for many less extreme stars. Instead, the continuum radiation that is observed originates over a finite radial range, where the optical depth in the relevant frequency bands declines from large values to values of order unity. Photons produce deeper inside diffuse outward through layers of gas whose density, temperature, and velocity change continuously with radius. The location that is conventionally identified as the stellar radius in atmosphere models is defined by a chosen reference optical depth in the continuum often expressed in terms of a Rossland mean optical depth of order 1. For R136c, this effective radius lies within the inner part of the wind where the flow has already accelerated significantly, but where the optical depth is still large enough that photons interact frequently with matter before escaping. The concept of an effective photosphere is therefore tied to radiative transfer rather than to a physically solid boundary. The radial stratification in the outer envelope is determined by the balance of forces and by the transport of energy. Closer to the star's center in the deeper layers that are still nearly hydrostatic gravity is balance by gas pressure and radiation pressure, and the density decreases inward to outward in a way that is set by the equation of hydrostatic equilibrium. As radius increases, the density declines, and the influence of radiation pressure becomes more important relative to gas pressure. For a star as luminous as R136c, the radiative acceleration in the outer envelope approaches a significant fraction of gravity, and near the sonic point where the local flow speed equals the sound speed, the radiative force begins to exceed the inward pull of gravity. Beyond this point, the gas is accelerated outward and becomes part of the supersonic wind. The envelope region around the sonic point and below the effective photosphere is therefore a transition zone in which the structure changes from nearly static to steadily outflowing. Opacity in the outer envelope and photosphere of R136c arises from several processes. Electron scattering provides a nearly frequency-independent contribution to the opacity in fully ionized hydrogen and helium. Bound-free and free-free absorption contribute additional frequency-dependent opacity, while numerous metal lines add strong peaks at specific wavelengths, particularly in the ultraviolet. At the metallicity of the Large Magellanic Cloud, the abundance of heavy elements is lower than in the solar neighborhood, so line and bound free opacity from metals is reduced compared with solar metallicity stars. However, the very high temperatures and ionization states in the envelope of R136c ensure that many ions still contribute significant opacity through their resonance and subordinate lines. The total opacity affects both the emergent spectrum and the efficiency with which radiation pressure can drive the wind. In regions where the opacity is dominated by electron scattering, the radiation field tends to be more nearly isotropic, while in regions where line opacity is important, the momentum transfer from radiation to gas is enhanced in specific frequency bands. The effective temperature of R136c, as quoted in atmosphere and evolutionary models, is defined by combining its luminosity with an effective radius through the Stefan-Boltzmann relation. In practice, this effective temperature is an average measure of the radiation field emerging from the extended atmosphere and does not correspond to a single physical layer with a unique local temperature. Model calculations for hydrogen-rich WN stars in the R136 core yield effective temperatures of the order of several tens of thousands of degrees Celsius, consistent with the strong ionization indicated by the spectrum. The uncertainties in extinction distance and model assumptions propagate into uncertainties in the exact numerical value, but all convergent solutions place R136c among the hottest stars known. The high effective temperature ensures that a substantial fraction of the stellar luminosity is emitted at extreme ultraviolet wavelengths, which are not directly observable because of interstellar absorption, but can be inferred from models constrained by the observed optical and ultraviolet spectrum. Because the effective photosphere is extended, the emergent continuum has properties that differ from those of a thin, sharp photosphere, as in classical plane parallel models. Limb darkening, the variation of intensity from the centers to the edge of the apparent stellar disk, is modified by the spherical geometry and by the presence of an outflowing atmosphere. Photons emerging along different lines of sight originate from different depths in the atmosphere, and the velocity field introduces Doppler shifts that vary with direction. In unresolved observations of R136c, these effects are not seen directly as spatial variations, but are encoded in the detailed shapes of spectral lines and in the overall flux distribution. Atmosphere models that treat the geometry as spherical and include the wind velocity field are therefore necessary to interpret the data correctly. Plane parallel models which assume a static thin photosphere are inadequate for a star with such an extended envelope and strong outflow. The thermal structure of the outer envelope is governed by radiative equilibrium to a good approximation, because convection is inefficient in these low-density, high-temperature layers. Energy generated in deeper regions flows outward in the form of radiation, and the temperature gradient adjusts so that the net flux is constant with radius. In the presence of an accelerating wind, adiabatic cooling due to expansion also contributes to the energy budget, particularly in the outer parts of the atmosphere. The combination of radiative and adiabatic processes defines the temperature as a function of radius, which in turn influences the ionization balance and line formation. For R136c, detailed models show that the temperature decreases gradually from very high values near the base of the atmosphere to lower values at large radii, but remains high enough throughout the line-forming region that hydrogen and helium are largely ionized, and that nitrogen is present in multiple ionization stages. There is ongoing theoretical work on whether very luminous stars like R136c develop inflated outer envelopes in which a region of reduced density extends the radius of the star beyond what would be expected from simple scaling relations. Such inflation can occur near opacity peaks associated with specific ions, for example ion group elements, where the local radiative acceleration approaches gravity and the density scale height increases. At the metallicity of the Large Magellanic Cloud, the strength of these opacity peaks and their effect on the envelope structure are somewhat reduced compared with solar metallicity. Nonetheless, models for very massive stars often predict some degree of envelope extension, which can increase the effective radius and lower the effective temperature for a given luminosity. Observationally, the presence or absence of an inflated envelope in R136c cannot be determined directly because the star is unresolved and its atmosphere is already extended by the dense wind. Instead, the issue is addressed by comparing the inferred effective temperatures and radii with predictions of different evolutionary and atmosphere models. At present, the available data are consistent with both moderately inflated and more compact solutions within the uncertainties. The definition of surface gravity in the context of R136c also requires care. In hydrostatic stars, surface gravity is expressed as the gravitational acceleration at the photospheric radius, and plays a key role in shaping the pressure scale height and line profiles. In a star with a strong wind and a blurred photosphere, the layers where most of the continuum and line formation occurs are not purely hydrostatic. Nonetheless, atmosphere models assign an effective gravity based on the underlying mass and radius, and include the counteracting radiative acceleration. The ratio of radiative to gravitational acceleration is often described by an Eddington factor. For R136c, this factor is inferred to be high indicating that radiation pressure strongly reduces the effective gravity in the outer envelope. This reduction in effective gravity contributes to the ease with which the wind is launched and affects the density stratification in the line-forming region. It also implies that small changes in luminosity or opacity can lead to significant changes in the force balance near the photosphere. Observational constraints on the effective radius and photospheric structure of R136c are indirect. The angular diameter of the star is far below the resolution of current optical interferometric techniques, at the distance of the Large Magellanic Cloud, so direct measurements of its size are not feasible. Instead, the radius is inferred from the combination of luminosity, effective temperature, and atmosphere model fluxes. The uncertainty in distance to the Large Magellanic Cloud, although relatively small compared with that for many other galaxies, still introduces an error in the derived radius. Extinction corrections and the adopted extinction law add further uncertainty. In addition, the presence of nearby luminous stars in the R136 core requires careful subtraction of blended light. Despite these challenges, analyses by different groups converge on radii consistent with those expected for very massive hot stars with extended atmospheres, reinforcing the internal consistency of the models. The extended envelope and blurred photosphere of R136c influence how its fundamental parameters are mapped to observational quantities. The luminosity effective temperature radius and surface abundances used in evolutionary calculations must be interpreted in light of the fact that the star's atmosphere does not have a simple static surface. Instead, a continuous transition exists from deep, nearly hydrostatic layers through an extended radiation-dominated envelope into a fast wind. The effective photosphere is the region where the continuum escapes, and where the atmosphere models match the observed spectral energy distribution. Its properties are therefore central to connecting observations with the deeper stellar structure, but they do not by themselves reveal the internal energy generation processes. Those processes take place in the underlying envelope and core, whose conditions must be inferred indirectly by combining the surface and wind properties with theoretical models of very massive star interiors. The chemical composition at the surface of R136c is inferred from detailed analysis of its emission line spectrum and provides information about the degree to which nuclear processed material has been mixed outward from deeper layers. In a baseline sense, stars in the Large Magellanic Cloud are expected to form with initial abundances that reflect the overall metallicity of this galaxy, which is lower than that of the solar neighbourhood by roughly a factor of a few in most heavy elements. Against this initial pattern, the present-day surface composition of R136c shows clear departures, particularly in the relative abundances of hydrogen, helium, carbon, nitrogen, and oxygen. These departures indicate that the outer layers now visible were once part of regions where hydrogen burning through the carbon-nitrogen-oxygen cycle has operated for a significant time, and that internal transport processes and mass loss have brought this material to the surface. The primary diagnostics of surface abundances in R136c are the strengths profiles and relative ratios of emission lines from hydrogen, helium, and nitrogen, together with weaker features from carbon and oxygen, where they can be measured. Because the spectrum is formed in a dense expanding atmosphere, the interpretation of these lines requires non-local thermodynamic equilibrium, atmosphere models that include the wind structure. In such models, the chemical composition enters as an input parameter that influences the ionization balance and line formation. By adjusting the mass fractions of hydrogen, helium, nitrogen, and other elements until the synthetic spectrum reproduces the observed line intensities and shapes, constraints on the surface abundances are obtained. For R136c, these analyses indicate that hydrogen remains present at the surface at a level lower than the initial value but still significant while helium is enhanced. This pattern is consistent with a star that has burned some fraction of its core hydrogen and has experienced mixing and mass loss, but has not yet lost its entire hydrogen-rich envelope. The absolute values of the hydrogen and helium mass fractions remain subject to modelling uncertainties, especially because clumping in the wind and blending of lines introduce degeneracies in the fits, but different studies converge on the conclusion that 136c is hydrogen-bearing rather than hydrogen-free. Nitrogen lines in the spectrum of R136c are strong and provide evidence for nitrogen enrichment at the surface. In the carbon-nitrogen-oxygen cycle, nitrogen builds up at the expense of carbon, and to a lesser extent oxygen, as hydrogen is fused into helium in the core. If material processed by this cycle is transported outward, the surface becomes enriched in nitrogen and depleted in carbon relative to the initial composition. Quantitative atmosphere models for R136c require nitrogen mass fractions that exceed those expected for an unprocessed Large Magellanic Cloud mixture, while carbon abundances must be reduced to match the weakness or absence of corresponding carbon lines. Oxygen abundances are less tightly constrained because many oxygen lines form in different parts of the atmosphere or are blended, but indications of some reduction relative to the initial value are consistent with the overall picture. The resulting abundance pattern with enhanced nitrogen and helium and reduced carbon is characteristic of matter that has been exposed to carbon-nitrogen-oxygen cycle processing. This pattern supports the view that the visible outer layers of R136c are not pristine, but are already chemically evolved compared with the initial composition. The presence of carbon-nitrogen-oxygen processed material at the surface implies that internal mixing processes operate efficiently in R136. In very massive stars, convection in the core extends over a large mass fraction, and boundaries between convective and radiative zones may be partially permeable because of overshooting and other hydrodynamic effects. Rotation can induce additional mixing through shear instabilities and meridional circulation, which transport angular momentum and chemical species between layers. When combined with continuous mass loss from the surface through the strong stellar wind, these processes can bring material from regions near the core outward into the envelope over relatively short timescales. In theoretical models of very massive stars at the metallicity of the Large Magellanic Cloud, this combination of mixing and mass loss can lead to quasi-homogeneous evolution, in which the star maintains a relatively uniform composition throughout much of its interior during core hydrogen burning. Whether R136c follows a fully quasi-homogeneous path or a more conventional one with a distinct composition gradient is not uniquely determined by current data, but the observed surface enrichment of nitrogen and helium shows that mixing is at least strong enough to erase the original outer layer composition. While hydrogen, helium, and nitrogen provide the clearest signatures, the behavior of other elements also carries information. The overall metallicity of R136c, as expressed by the abundances of iron group elements and other heavy species that dominate line opacity in the ultraviolet, is consistent with that of the Large Magellanic Cloud interstellar medium within uncertainties. These elements act primarily as opacity sources and do not participate directly in the carbon-nitrogen-oxygen cycle. Their abundances influence the strength of the line-driven wind and the detailed structure of the outer envelope, but do not show large changes associated with hydrogen burning. As a result, atmosphere models for R136c typically adopt baseline Large Magellanic Cloud values for these species, and vary only the light elements most affected by nuclear processing and mixing. This approach is adequate for reproducing the observed spectrum and is compatible with a scenario in which the star has undergone internal mixing and surface enrichment in light elements, while retaining the global heavy element pattern of its birth environment. The surface composition inferred for R136c has direct consequences for its wind and for the chemical enrichment of its surroundings. The enhanced helium and nitrogen content of the outer layers means that the material carried away by the wind is correspondingly enriched in these elements, compared with the original interstellar medium. Over the lifetime of the star, the integrated mass lost in the wind represents a non-negligible contribution of helium and nitrogen-rich gas to the local environment. This gas mixes into the ionized and later cooled components of the cluster medium and the wider Tarantula Nebula, contributing to the gradual buildup of nitrogen and helium in subsequent generations of stars that may form from this material. At the same time, the fact that hydrogen remains abundant at the surface indicates that the star has not yet reached the later evolutionary phases in which hydrogen is largely absent, and heavier elements such as carbon and oxygen become more prominent in the wind. The currently observed composition thus reflects an intermediate state in which the star is still dominated by hydrogen burning, but has already altered its outer layers through nuclear processing, mixing, and mass loss. In summary, the surface composition and mixing signatures of R136c, as inferred from its emission line spectrum and atmosphere modelling point, to a very massive star that has begun to reveal products of core hydrogen burning at its surface while still retaining a substantial hydrogen-rich envelope. The combination of helium and nitrogen enhancement carbon depletion and approximately Large Magellanic Cloud metallicity in heavier elements is consistent with expectations for a young, very luminous star undergoing strong internal mixing and mass loss in a low metallicity environment. These surface properties form an essential observational link between the outer atmosphere and the deeper interior where the bulk of the nuclear energy generation occurs. The deep interior of R136c contains the central region, where nuclear energy generation through hydrogen fusion proceeds at a rate sufficient to support the star's very high luminosity. In a very massive star of this kind, the core occupies a large fraction of the total stellar mass and radius compared with less massive stars. The core is characterized by high temperatures of the order of tens of millions of degrees Celsius and high densities that are many times higher than those in the outer envelope. Under these conditions, hydrogen fusion proceeds predominantly through the carbon-nitrogen-oxygen cycle, rather than through the proton-proton chain that dominates in lower mass stars. The carbon-nitrogen-oxygen cycle uses pre-existing carbon-nitrogen and oxygen nuclei as catalysts to convert hydrogen into helium-releasing energy in the form of gamma-ray photons and neutrinos. The rate of energy generation in this cycle depends strongly on temperature increasing rapidly, with even modest increases in core temperature, so the central conditions of R136c are such that the carbon-nitrogen-oxygen cycle is highly efficient. In the carbon-nitrogen-oxygen cycle, a sequence of reactions transforms hydrogen nuclei into helium nuclei, while cycling carbon, nitrogen, and oxygen nuclei through different isotopic states. At the temperatures in the core of R136c, the slowest reaction in the sequence, which usually sets the overall timescale of the cycle, proceeds at a rate sufficient to sustain the required energy output. Because the cycle is very temperature sensitive, the core structure adjusts so that the energy generation rate balances the energy that must be transported outward to match the observed luminosity of the star. If the temperature were significantly higher, the energy generation rate would increase steeply, raising the luminosity and driving expansion of the core until the temperature decreased again. If the temperature were lower, the energy generation rate would fall, the core would contract under its own gravity, and the temperature would rise until equilibrium was restored. In this way, the core settles into a state where hydrostatic equilibrium and energy balance are maintained with the carbon-nitrogen-oxygen cycle, providing the dominant contribution to energy generation. The energy released by nuclear fusion in the core of R136c is transported outward primarily by radiation rather than by conduction. In very massive stars, the energy density in radiation is high, and radiation pressure contributes significantly to the total pressure. Opacity in the core is dominated by electron scattering and by contributions from bound free and free-free processes involving ionized hydrogen and helium, with heavy elements adding smaller corrections. The mean free path of photons is very short, so energy diffuses outward through a large number of scattering and absorption events. The timescale for photons to travel from the core to the surface is long compared with dynamical timescales, but short compared with the nuclear timescale over which hydrogen is consumed. Neutrinos produced in some reactions of the carbon-nitrogen-oxygen cycle escape directly because they interact only weakly with matter, but at core temperatures typical of hydrogen burning, their contribution to the total energy loss is small compared with photon energy transport. The inner regions of R136c are expected to be convective over a substantial volume because of the steep temperature dependence of the energy generation rate and the high luminosity that must be carried outward. When the radiative temperature gradient required to transport the luminosity exceeds the adiabatic gradient, the gas becomes unstable to convection. In very massive stars, this condition is satisfied over a large central region, producing an extended convective core. Within this core, energy and chemical species are transported by bulk motions of material, and the composition tends to be nearly uniform. Hydrogen is consumed and helium is produced throughout the convective core, while carbon, nitrogen, and oxygen participate in the catalytic cycle. The presence of an extended convective core in R136c is consistent with the observed surface enrichment in nitrogen and helium, and with theoretical models that predict strong internal mixing in very massive stars. Above the convective core there is a radiative envelope where convection is less important, and energy transport is dominated by radiation. The structure of the core is determined by the interplay between gravity gas pressure and radiation pressure. In very massive stars such as R136c, radiation pressure contributes a large fraction of the total pressure in the deep interior. The pressure support can be expressed as the sum of gas pressure arising from the motion of ions and electrons, and radiation pressure arising from the momentum carried by photons. The ratio of radiation pressure to gas pressure increases with temperature and luminosity, and with stellar mass. In the core of R136c, this ratio is high, meaning that radiation pressure plays a central role in counteracting gravity. The degree to which radiation pressure dominates affects the density profile and the response of the star to perturbations. A core that is strongly supported by radiation pressure tends to be more extended, and to have a density profile that is less centrally peaked than one dominated by gas pressure alone. This structure influences how the star evolves in response to changes in composition and energy generation as hydrogen is converted to helium. The nuclear timescale for hydrogen burning in the core of R136c can be estimated by dividing the energy available from converting hydrogen to helium by the luminosity. For a very massive star with a luminosity of several million times the luminosity of the Sun, this timescale is relatively short compared with that of lower mass stars of the order of a few million years. This short timescale is consistent with age estimates for R136c and the surrounding cluster. During this period, the central hydrogen abundance decreases while the helium abundance increases. At early times, the core is nearly homogeneous in composition because of convection, but as evolution proceeds, gradients can develop at the boundary between the convective core and the radiative envelope, depending on the efficiency of mixing processes such as overshooting and rotationally induced transport. The exact extent of the convective core and the profile of hydrogen and helium abundances through the interior are key outputs of stellar evolution models and influence predictions for later evolutionary stages. Rotational effects can further modify the internal structure and core conditions of R136c. If the star rotates rapidly, centrifugal forces reduce the effective gravity near the equator and can alter the shape of the equipotential surfaces. Rotation also drives large-scale circulation currents that transport angular momentum and chemical species between different layers. In combination with convection, these processes can increase the degree of mixing between the core and the envelope. For very massive stars at the metallicity of the Large Magellanic Cloud, evolutionary models often explore cases in which rotation is strong enough to approach quasi-homogeneous evolution, in which the composition remains nearly uniform throughout the star for a significant fraction of the hydrogen-burning lifetime. Whether R136c follows such a path depends on its initial rotation rate and on the brake provided by wind mass loss, but the observed surface composition suggests that mixing is efficient. Regardless of the exact rotation speed, the core must maintain conditions that are compatible with the observed luminosity, and surface abundances and models that match these properties always include a central region where the carbon-nitrogen-oxygen cycle is the dominant energy source. The equation of state in the deep core of R136c is that of a hot, fully ionized plasma, in which ideal gas behavior is modified by radiation pressure and at very high densities by partial electron degeneracy. At the temperatures characteristic of core hydrogen burning, electron degeneracy pressure is relatively unimportant compared with gas and radiation pressure, so the dynamics of the core are governed primarily by classical thermodynamic quantities. As hydrogen is depleted and helium accumulates, the mean molecular weight of the plasma increases, altering the relationship between temperature, pressure, and density. This change in mean molecular weight influences the thermal structure and can drive further adjustments in the core to maintain hydrostatic equilibrium and energy balance. The gradual buildup of helium and the associated changes in core structure are precursors to later phases of evolution, but during the hydrogen burning stage, the core remains in a relatively stable configuration. The modeling of R136c's core relies on stellar evolution codes that solve the equations of stellar structure, including hydrostatic equilibrium, energy generation, energy transport, and composition changes, with input physics appropriate for very massive stars at the metallicity of the Large Magellanic Cloud. These models are constrained by observational estimates of the star's luminosity, effective temperature, surface composition, and when available rotation. By locating R136c on the theoretical Hertzsprung-Russell diagram and matching its surface abundances, modelers infer the central hydrogen fraction, the core mass, and the age within the hydrogen burning phase. In typical solutions, the core contains a large fraction of the total stellar mass and remains convective throughout most of the hydrogen burning lifetime. The central hydrogen fraction decreases from its initial value to progressively lower values as the star ages, while the central helium fraction increases. The carbon-nitrogen-oxygen catalyst abundances adjust to their equilibrium ratios within the core, setting the energy generation rate per unit mass. Uncertainties in the internal structure of R136c arise from uncertainties in several physical inputs and assumptions. These include the treatment of convective boundaries and overshooting the efficiency of rotational mixing, the prescription for mass loss, and the opacity at high temperature and low metallicity. Variations in these inputs can change the size of the convective core, the central temperature and density, and the overall hydrogen burning lifetime. Nonetheless, across a wide range of plausible models, the core of R136c is consistently described as a region of high temperature and high density, where hydrogen is converted into helium predominantly through the carbon-nitrogen-oxygen cycle, where radiation pressure contributes strongly to support against gravity, and where convection ensures substantial mixing of energy and composition. These generic features define the deep interior of the star during the hydrogen burning stage and provide the physical foundation for understanding its extreme luminosity and its position on the Hertzsprung-Russell diagram. In a star as luminous and massive as 136c, radiation pressure plays a dominant role in the global force balance and brings the star close to what stellar structure theory calls the Eddington limit. This limit is the luminosity at which the outward force exerted by radiation on the atmospheric gas, mainly through scattering by free electrons, equals the inward force of gravity. When a star operates near this regime, small changes in luminosity or opacity can have large effects on the outer layers. For R136c, the combination of very high luminosity and low to moderate metallicity implies a high ratio of radiative to gravitational acceleration in the envelope and atmosphere. This ratio, often expressed as an Eddington factor, is inferred from atmosphere and evolutionary models that match the observed luminosity, effective temperature, and surface composition. These models indicate that R136c has an Eddington factor substantially larger than those of less massive O-type stars and comparable to values found in the most luminous hydrogen-rich Wolf-Rayet stars. As a result, the effective gravity in its outer layers, defined as the difference between gravitational and radiative accelerations, is reduced, and this reduction strongly affects both the envelope structure and the wind. The influence of radiation pressure on the envelope can be described by examining how the local radiative acceleration varies with depth. In deep layers where densities are high and opacity is dominated by electron scattering and continuum processes, the radiative acceleration is proportional to the local flux and to the opacity per unit mass. Because the flux increases toward the center and the opacity is relatively uniform, the inner regions can remain well below the local Eddington limit, even in a very luminous star. In contrast, in the outer envelope, where densities are lower and opacity contributions from specific ions and spectral lines become important, the ratio of radiative to gravitational acceleration can approach or exceed unity over limited ranges of temperature and density. These zones often coincide with opacity peaks associated with partially ionized heavy elements. When the radiative acceleration in such a zone nearly balances gravity, the local density scale height increases and the envelope can become extended. In models of very massive stars similar to R136c, this effect produces a region of reduced density at the base of the atmosphere, sometimes described as envelope inflation. Although the degree of inflation depends on metallicity and on the detailed opacity profile. Near the sonic point, where the outflow transitions from subsonic to supersonic speeds, the balance between gravity and radiation pressure is particularly important. The wind of R136c is launched from layers in which the radiative acceleration slightly exceeds gravity, once line opacity is taken into account. In line-driven wind theory, metal ions in the atmosphere absorb and scatter photons in many lines, providing additional channels for momentum transfer beyond electron scattering. The cumulative effect of these lines increases the radiative acceleration in the outer layers. For a star near the Eddington limit, only a modest enhancement of the radiative force above the electron scattering value is needed to overcome gravity and drive a strong outflow. In this way, the proximity of R136c to the Eddington limit helps to explain why its mass loss rate is high and why its wind reaches large terminal velocities even at the metallicity of the Large Magellanic Cloud. Atmosphere models that couple the wind to the underlying envelope must therefore treat the radiative acceleration consistently, including both continuum and line contributions to reproduce the observed wind properties. The reduced effective gravity in the outer layers of R136c has further consequences for stability. When the Eddington factor approaches unity in parts of the envelope, the star becomes more susceptible to instabilities that can perturb the density and velocity structure. Linear stability analyses and numerical simulations of very massive stars predict that regions with high radiative acceleration can develop spatial and temporal fluctuations leading to density inhomogeneities and subphotospheric motions. In an atmosphere with a strong wind, these fluctuations can seed the clumping observed in the outflow and may contribute to variability in emission line strengths and profiles. For R136c, observational evidence for variability is limited by crowding and by the available time sampling, but any detected changes in wind diagnostics over time are interpreted within this framework of near Eddington instability and line-driven wind structure. These processes operate on timescales shorter than the nuclear timescale and do not alter the global hydrostatic structure of the star, but they do affect the detailed stratification and the flow of material through the outer envelope into the wind. The near Eddington state also influences the mapping between fundamental stellar parameters and observable quantities such as effective temperature and radius. In classical stellar structure, models a given core mass and energy generation rate lead to a relatively tight relation between luminosity radius and effective temperature. In a star close to the Eddington limit, changes in opacity or composition in the outer envelope can shift this relation, because small adjustments in local conditions can lead to significant changes in the density and radius of the envelope. For R136c, evolutionary tracks computed with different assumptions about envelope physics, mass loss and mixing can yield somewhat different effective temperatures and radii for the same core properties, even while reproducing the observed luminosity. This sensitivity contributes to the spread in model-derived effective temperatures reported for very massive WN stars in R136. Despite these differences, all successful models require that the luminosity be a large fraction of the Eddington luminosity, reinforcing the view that radiation pressure is a dominant factor in the star's structure. From the perspective of the surrounding cluster and nebula, the near Eddington nature of R136c is reflected in its strong radiative and mechanical feedback. When R136c is considered together with other very luminous stars in the R136 core, the combined effect of their near Eddington luminosities is the establishment of an intense radiation field and a network of wind-driven structures in the central Tarantula Nebula. From the internal point of view of the star, the essential consequence is that the core envelope and atmosphere must maintain a configuration in which radiation pressure and gravity are closely balanced, providing the structural context in which the subsequent evolutionary phase of R136c proceeds. The current evolutionary stage of R136c is constrained by its luminosity, effective temperature, surface composition, spectral classification and membership in the very young core of R136. When these observables are compared with theoretical evolutionary tracks for very massive stars at the metallicity of the Large Magellanic Cloud, they indicate that R136c is still in the core hydrogen burning phase and is therefore on an extended version of the main sequence, even though its spectrum already shows the features of a hydrogen-rich Wolf-Rayet star. Models that reproduce its position in the Hertzsprung-Russell diagram and its surface nitrogen and helium enrichment do so at ages of order a few million years consistent with independent age estimates for the R136 core. At such ages, very massive stars have converted a significant fraction of their initial core hydrogen into helium, but retain enough hydrogen in their interiors and envelopes for hydrogen fusion through the carbon-nitrogen-oxygen cycle to remain the dominant energy source. Thus, R136c is interpreted as a very massive core hydrogen-burning star that has entered a Wolf-Rayet spectral regime early in its life because of strong mass loss and efficient internal mixing. From the point of view of stellar structure, the inferred evolutionary stage implies that R136c continues to possess a large convective core containing most of the stellar mass surrounded by a radiative envelope that has been partially stripped and mixed. The central hydrogen mass fraction is expected to be lower than its initial value, but not yet exhausted, and the central helium fraction has increased accordingly. The presence of strong nitrogen enrichment and helium enhancement at the surface, together with residual hydrogen, suggests that mixing mechanisms such as convection overshooting and rotationally induced transport have redistributed material between the core and envelope while the star remains on the hydrogen-burning sequence. Evolutionary models that incorporate such mixing reproduce the observed abundance pattern when evaluated at an age that matches the cluster age. In these models, the star's position in the luminosity temperature plane shifts gradually toward lower effective temperature and higher luminosity as the mean molecular weight in the core increases, but during most of the hydrogen burning stage it remains extremely hot and luminous, as observed for R136c. The present-day mass of R136c is less directly constrained than its luminosity and effective temperature, but its evolutionary state places some limits. Atmosphere modeling and evolutionary tracks that match the observed luminosity suggest current masses of at least around 100 times the mass of the Sun, and possibly more than 200 times the mass of the Sun. The fact that the star shows evidence of processed material at the surface and a strong wind implies that it has already lost part of its initial mass. The amount of mass loss that has occurred by the present stage depends on the adopted mass loss prescriptions, clumping factors and the duration of the hydrogen burning phase to date. For plausible assumptions, the initial mass is inferred to have been higher than the present mass by several tens of solar masses, but the exact value remains uncertain. Regardless of the precise numbers, the current evolutionary stage can be summarized as one in which R136c remains extremely massive, has already undergone substantial but not catastrophic mass loss, and continues to generate most of its luminosity through core hydrogen fusion. The possible binarity of R136c adds complexity to the determination of its evolutionary stage, but does not alter the broad conclusion that the system is very young and dominated by hydrogen burning. If R136c consists of two massive stars in a close binary, each component would follow its own evolutionary track, with mass and luminosity somewhat lower than those inferred for a single star that produces the same combined light. In such a scenario, interaction between the stars, including wind collision and possible mass transfer, could modify the surface compositions and mass loss histories, compared with isolated stars of the same initial mass. However, given the very young age of the R136 core, any major binary interaction affecting the internal structure is likely to be in its early stages. Observationally, the presence of hydrogen-rich Wolf-Rayet spectra and high luminosities in several R136 members, whether single or binary, points to a population of very massive stars that have entered similar spectral phases at roughly the same cluster age. For the purposes of describing the current evolutionary state, R136c can be treated as a luminous hydrogen burn system whose detailed internal configuration remains uncertain, but whose global properties match those of early Wolf-Rayet phase evolution. Comparisons with other very massive stars in R136 help to place R136c within a sequence of evolutionary stages at fixed cluster age. Stars classified as the most luminous WNH objects in the core show similar effective temperatures, luminosities, and surface enrichment patterns suggesting that they occupy comparable evolutionary states. Some neighbouring stars with slightly lower luminosities and weaker nitrogen enrichment may be less evolved, having experienced less mixing and mass loss. Others that show stronger signs of processed material and somewhat different temperatures may be further along the hydrogen burning track, or may have experienced different rotational histories. Within the uncertainties, 136c appears representative of the upper end of this population, rather than an extreme outlier. Its parameters lie within the envelope of solutions provided by models for very massive stars at the observed cluster, age reinforcing the conclusion that it is a typical example of a young, extremely massive hydrogen-burning star that has entered a Wolf-Rayet spectral regime. The current evolutionary stage of R136c also has implications for its rotational properties. If the star began its life with a high rotation rate, as many massive stars are thought to do, internal angular momentum transport and wind mass loss will have modified its rotation profile over time. Strong winds remove angular momentum from the outer layers and tend to spin down the surface, while internal transport can redistribute angular momentum between the core and envelope. Observational constraints on the present rotation of R136c are limited because broad emission lines and wind effects mask the photospheric features that are usually used to measure projected rotational velocities. Nevertheless, evolutionary models that match its luminosity and surface composition often require moderately rapid rotation earlier in its life to achieve the degree of mixing implied by the nitrogen and helium enrichment. At the current stage, the surface may rotate more slowly than the core, and the star as a whole may occupy an intermediate regime between solid body rotation and strong differential rotation. These details are not directly observable, but are relevant for predictions of later evolutionary behavior. Another aspect of the current stage concerns the balance between mass loss and internal structural adjustment. As R136c continues to lose mass through its dense wind, the envelope responds by contracting or expanding, depending on how the mass loss alters the relation between luminosity mass and mean molecular weight. In models, the star adjusts quasi-statically, preserving hydrostatic balance at each stage while the internal composition evolves. Because the hydrogen-burning lifetime is short of order, a few million years, the time derivative of global parameters such as luminosity and effective temperature is relatively large compared with that of lower mass stars, but on observational timescales of years to decades the changes are extremely small. Thus, 136c can be treated as being in a quasi-steady evolutionary phase in which its global parameters are approximately constant, even though over its full hydrogen-burning lifetime they will change significantly. The current observational snapshot corresponds to a specific point along this sequence, with a well-developed convective core, a partially processed envelope, and a strong wind. Finally, the present evolutionary state of R136c sets the initial conditions for its subsequent evolution into more advanced stages. The core mass, central hydrogen fraction, rotation profile, and envelope mass and composition at this stage determine how the star will evolve once core hydrogen is depleted. While the detailed future path involves uncertainties related to mass loss mixing and possible binary interactions, the essential point is that R136c is currently in a phase where its structure is dominated by core hydrogen burning, under conditions of high radiation pressure, strong winds, and significant surface enrichment in helium and nitrogen. Any later transition to core helium burning and to more heavily stripped configurations will proceed from this starting configuration. For now, observational evidence and theoretical models agree that R136c is best described as a very young, extremely massive hydrogen-burning star in a hydrogen-rich Wolf-Rayet phase, with properties that are broadly consistent with those predicted for such objects in a low metallicity, high-density cluster environment, like the R136 core in the Tarantula Nebula. The future evolution and possible end states of R136c are inferred entirely from theoretical models of very massive stars constrained by the present-day properties of the star and by the metallicity and environment of the Large Magellanic Cloud. Direct observation of its later stages is not possible on human timescales, so the discussion necessarily relies on model sequences that begin with masses comparable to the current estimates for R136c and evolve them forward under different assumptions about rotation mass loss and eternal mixing. In such models, the immediate next phase after the current hydrogen burning stage involves gradual exhaustion of hydrogen in the convective core. As the central hydrogen mass fraction declines towards zero, the core contracts and heats while the envelope responds by adjusting its radius and temperature so that the star remains in hydrostatic and thermal equilibrium. The luminosity remains high and may increase modestly because of the rise in mean molecular weight in the core, while the effective temperature can shift depending on the details of envelope inflation, wind mass loss and opacity. Once core hydrogen is exhausted, the central regions of R136c are expected to transition to core helium burning. In this phase, helium is fused into carbon and oxygen through the triple alpha process and subsequent alpha capture reactions. The core again reaches a stable configuration in which nuclear energy generation balances energy losses and supports the weight of the overlying layers. The exact structure at the onset of helium burning depends sensitively on the amount of mass lost during the preceding hydrogen burning phase and on the efficiency of mixing. If mass loss and mixing have reduced the hydrogen-rich envelope substantially, the star may already resemble a more classical hydrogen, poor Wolf-Rayet object by the time core helium burning begins, with surface abundances dominated by helium and heavier elements and only traces of hydrogen. If instead a significant hydrogen envelope remains, the star may continue to show a hydrogen-rich spectrum for some part of the helium burning phase before further mass loss strips the outer layers. In either case, the surface remains enriched in products of earlier nuclear burning, and the wind continues to be strong, although its detailed properties evolve with the changing surface composition and luminosity. During core helium burning, the interior of R136c develops a stratified structure in which different nuclear burning products occupy distinct radial zones. The helium-burning core produces carbon and oxygen, while surrounding shells may continue to burn hydrogen if any hydrogen-rich layers remain at appropriate temperatures and densities. As evolution proceeds, helium is gradually depleted in the core, and the central composition becomes dominated by carbon and oxygen. Further contraction of the core leads to higher temperatures and the ignition of advanced burning stages in massive star models, including carbon, neon oxygen, and silicon, burning each operating over progressively shorter timescales and smaller regions. For stars in the mass range inferred for R136c, these later stages are expected to be rapid compared with the hydrogen and helium burning phases occupying only a small fraction of the total stellar lifetime. Because these stages occur at high densities and temperatures deep inside the star, they are not directly observable, and their properties are inferred from stellar evolution calculations that include appropriate nuclear reaction networks and equations of state. A key question for very massive stars such as R136c is whether the final core mass and structure at the end of silicon burning fall into a regime where pair production effects significantly modify the evolution, or whether the star instead follows the more familiar core collapse pathway. In pair instability scenarios which are predicted for helium core masses, above a certain threshold, the creation of electron-positron pairs at high temperatures reduces radiation pressure support and can lead to dynamical instabilities, partial disruption, or complete disruption, without a compact remnant depending on core mass. At the metallicity of the Large Magellanic Cloud, however, strong winds during the hydrogen and helium burning phases can substantially reduce the final helium core mass of very massive stars. Many model sequences for initial masses broadly consistent with those estimated for R136c yield final core masses below the range, where complete pair instability disruption is expected, favouring an outcome in which the star undergoes gravitational core collapse and leaves behind a black hole. This conclusion remains model-dependent because it is sensitive to mass loss prescriptions, clumping factors in the wind, rotational mixing, and possible binary interactions, all of which affect the final core mass and entropy profile. If R136c ends its life through core collapse, the final stages would involve the formation of an iron-rich core that becomes dynamically unstable when it exceeds the maximum mass that can be supported by electron degeneracy pressure and thermal pressure. The core then collapses on a dynamical timescale, and the outcome is either the formation of a neutron star with an outgoing shock that expels the surrounding layers, or more likely for very massive stars the direct or nearly direct formation of a black hole. In the latter case, much of the stellar envelope can fall back onto the newly formed black hole, and the observable electromagnetic display may be weak compared with that of typical core collapse supernovae. Some theoretical models propose that under certain conditions, for example, high rotation and specific angular momentum distributions, the collapse of a very massive star could produce highly energetic transients associated with relativistic jets, but the applicability of such scenarios to stars like R136c is uncertain and remains an active area of research. What most models agree on is that the remnant of a star with a final core mass in the range expected for R136c will be a black hole potentially with a mass of several tens of times the mass of the Sun, or more depending on how much material is ejected versus accreted during and after collapse. Binary evolution pathways introduce further variability into the range of possible end states. If R136c is part of a close binary system, mass transfer, common envelope evolution, or merger events can alter its mass angular momentum and core structure before collapse. Mass transfer from R136c to a companion could strip its envelope more efficiently than winds alone, producing a more compact Wolf-Rayet star with a smaller radius and different surface composition by the time of core collapse. Conversely, if R136c were to accrete material from a companion in certain evolutionary phases, its core mass and rotation profile could be modified in ways that change its final fate. In some scenarios, binary evolution in a dense cluster core like R136 can produce pairs of massive black holes that eventually merge through gravitational wave emission. Whether R136c itself will follow such a pathway cannot be determined from current data, but the possibility is considered in population synthesis models that attempt to connect very massive stars in young clusters with the black hole mergers observed by gravitational wave detectors. Because the final evolutionary stages of R136c occur on timescales, orders of magnitude longer than human observational baselines, and because key parameters such as the exact mass loss history rotation and binary status remain uncertain, predictions of its detailed end state must be regarded as approximate. Nevertheless, some robust general statements can be made. R136c is likely to continue its evolution through core helium burning and subsequent advanced burning stages as a very massive luminous star, with a strong wind progressively exposing more heavily processed material at its surface. Its final core is expected in many models to be massive enough to collapse into a black hole, rather than a neutron star with a remnant mass that depends on the efficiency of mass ejection during collapse. Whether the collapse is accompanied by a bright supernova, a relatively faint transient or a largely hidden event, depends on how the outgoing shock interacts with the overlying layers and on the degree of fallback, both of which are sensitive to internal structure details that are not directly observable. In summary, theoretical models of very massive star evolution at Large Magellanic Cloud metallicity suggest that R136c will follow a sequence from core hydrogen, burning through core helium burning, with an increasingly stripped envelope to a final phase in which an evolved compact core undergoes gravitational collapse and likely forms a black hole. The possibility of pair instability-related phenomena or of outcomes modified by binary interaction cannot be excluded but requires specific combinations of initial mass-mass loss rotation and orbital parameters that are not yet well constrained for this object. As a result, current descriptions of the later evolution and end states of R136c emphasize ranges and scenarios rather than precise predictions, while consistently identifying it as a progenitor of a massive compact remnant whose detailed properties will reflect the integrated effects of mass loss mixing, and if present binary evolution over its relatively short lifetime as a very luminous star.